All right, so now we have to discuss what happens when we have a poorly behaved mass spectrum. By poorly behaved, we mean simply that our number of carbon calculation doesn't work. We can't simply do that m plus 1 divided by the m divided by 1.1 times 100 trick to get our molecular formula. Typically, your number of carbon calculation doesn't work for one of two reasons. Either, quite simply, there is just no m plus 1 peak, all right, or you do have an m plus 1 peak. You try to do your number of carbon calculation, but your number of carbon calculation gives an unreasonable answer. You know, you punch everything into your calculator and it tells you got 50 carbons or something, even though your molecular ion is at 74 m over z. That doesn't make any sense, right? So these would be the reasons that we would not be able to use that calculation, and that's what I mean by a poorly behaved spectrum. Okay, so we are going to see certain functional groups tend to always give us poorly behaved spectrum. All right, and the reason for that is that these functional groups, they just cause the molecule to fragment quite easily. So you don't actually get many or none intact molecular ions that make it to the end of the detector. All right. So these functional groups, they cause this molecule to kind of split up, but they do it in some, what am I thinking? There's a pattern to it that we see. All right. So, for example, alcohols, especially larger alcohols, they will give you poorly behaved mass spectrum. All right. Other functional groups are esters. They also break apart quite easily, and alkyl halides. All right. So let's take these one by one here. So alcohols actually fragment differently depending on whether you have a primary alcohol versus a secondary or tertiary. Primary alcohols will lose water. Water has an m over z equal to 18. So you don't really see very much, if any, of your molecular ion peak. So let's look at an example here. Here's my molecular ion peak at 74. We got basically nothing. Very, very low signal, and importantly, we don't have an m plus 1 peak. What we do have is this very prominent peak here at 56. Okay, so I'm sort of scanning this way here and looking for something relatively intense in my spectrum here. The first big one that I see is this peak at 56, all right? So this is my loss of water peak, all right? So how are we going to analyze our poorly behaved spectrum, all right? So for every poorly behaved mass spectrum, what do we need? So this is our analysis that we need to have in our notebooks. First of all, we're still going to identify that m plus 1 peak. So in this, that molecular ion peak. So in this case, my molecular ion is again at 74. I can't stress enough how much that in and of itself is a really big piece of information. All right. If you know your functional group is an alcohol, which we do because we've taken our IR spectrum, right? So I know I have that alcohol peak in there. All 2 carbon alcohols have the same molar mass. All 3 carbon alcohols, all 4 carbon alcohols, right? So there's some like really simple guess and check that you can do to get at your molecular formula here. So just having that molar mass is pretty significant in and of itself. But what we're going to do for our poorly behaved mass spectrum, since we can't get that number of carbon calculation, is what I'm going to call fragment identity. We got to look elsewhere in our spectrum and be able to point out a fragment in our spectrum, right? So for example, what I would do for this one is I would say, okay, well, my 56 m over z, this corresponds to my molecular ion peak minus 18, which is a loss of water. All right, so we just need to identify one of our fragments. If we can get a few of them, that's even better. But we just need to identify at least one fragment in our spectrum here for our poorly behaved mass spectrum, right? So you're going to give me you're still going to identify that molecular ion peak, but then you're going to identify a fragment in there, right? In this case, we see this loss of water peak. So then at the end of the day, we're still going to get to what we need from our mass spectrum, which is our molecular formula. All right, so I have this loss of water peak here. Where do I go from there? So if we think about it, let's just draw like a random structure here. This is going to be way too big. All right, but if I lose water, what that means is my primary alcohol has lost this bond right here. That bond is broken. That OH has fallen off. And for whatever reason, when that leaves, it takes one of these neighboring hydrogens with it. Okay, so that's how I get that M over Z of 18 that's lost. An oxygen and 2 hydrogens. So if we look elsewhere on our primary alcohol, what we want to note is we see this sort of pattern with regard to our carbons. This methyl group at the end has a mass number of 15. Everything in the middle here will average out to a mass of 14, even if you have branch points in there, right? Okay, the average will be that 14. And over here, because I lost that water, this carbon actually only has a mass number of 13. So everything here, on average, is 14. I can use that fact. I can take my 56 divided by that 14, and I get 4. Right? I figured out how many of these little carbon-hydrogen building blocks there are that make up my primary alcohol. Again, guessing and checking would have worked just as well, all right? But just to sort of have a little bit more guidance there, we can think about it this way as well. We can get our approximate number of carbons by taking that loss of water peak and dividing it by 14. So at the end of the day here, we're going to get our molecular formula. Okay. If we have our 74 minus the number of carbons minus the number of oxygens, that's 74 minus 4 times 12 minus 16. And we get 10. So C4H10O. Secondary alcohol, secondary and tertiary, they lose alkyl groups. All right, so it's again that carbon-oxygen bond that's kind of the problem here. Let's just take a look. Again, I'm going to make one that's a little bit too big just so we can sort of practice here. So now I have a secondary alcohol. These will break off over here and over here. So I'll end up seeing these fragments that correspond to the loss of these alkyl groups here. So in this case here, if I have a molecular ion, but it's really small. I don't have my M+1. I'm going to start scanning this way. The first thing I see, and it's not that big, so maybe I'd skip over it. In this case, it's pretty meaningful though. This would be my M-15. Remember, 15 is the size of a methyl group. So again, fragment identity. First, I'm going to do my M plus, is that 74? But when it comes to my fragment identity, I have a loss of a methyl group here, right? So 59 M over Z, that's my molecular ion minus 15, loss of methyl. And I can actually sort of go the biggest peak here, what we would call the base peak, the biggest peak in your spectrum, this M over Z of 45. Well, 74 minus 45 gives us 29. What's 29? 15 plus 14, or the loss of an ethyl group. So I can also identify 45 M over Z, M minus 29, loss of ethyl. Whoops. All right, so I have my alcohol, this one was too big. On one side, when it broke apart, I lost a methyl group. On the other side, when it broke apart, I lost an ethyl group. So I can get to my molecular formula here. Again, my C4, we can punch it into our calculator. It's actually the same mass number as above, so we can kind of reason it's going to be the same calculation as up here. C4, H10O. So this is actually the same molecular formula, but a different alcohol, and you can see that because of that, we got a different fragmentation pattern. This sort of gives you a clue about how our database in our mass spec is able to uniquely identify molecules, right? Even though these had the same molecular formula, they have this unique fragmentation pattern. For esters, we're going to see something similar. These often do not make it intact to the end of our detector, especially the larger ones. But they have a tendency to break at predictable places. This bond right here is really, really common to see break, right? So you very rarely get intact molecular ion peaks of your esters, but instead you can actually find both this fragment and this fragment in your mass spectrum. This fragment right here tends to be smaller because this bond right here can also break, so we sort of sometimes see without the oxygen as well. But I think this is going to be the first thing I'm going to look for, is one of the both of those two peaks on my spectrum. All right, alkyl halides. We know we studied alkyl halides, so for example, these just random examples here. These are the two that we're going to see the most, alkyl chlorides and alkyl bromides. That halogen carbon bond is really weak. So these tend to break right at that halogen carbon bond. All right. For alkyl halides, we will often see molecular ion peaks. We just won't see our M+1 peak. They're always very low in intensity. All right. So this would be an example here. Yes, we see a molecular ion peak, but we do not see any M+1 peak, so we can't really do our calculation. All right. Now, importantly, these have a unique signature here that makes it so we can identify our alkyl halides using mass spec. And this is actually really helpful because we can't identify alkyl halides using IR. These are one of our functional groups that don't actually show up on an IR spectrum. They look just like alkanes. So instead, we have this special M, and not M+1, but M+2 pattern that we see here. All right, so if we look on our alkyl halide spectrum again, I don't have an M+1, I have an M and an M+2. That is this unique signature of an alkyl halide. For alkyl halides, that's the reason is because there are two isotopes of these halogens that differ by a mass number of 2. So for chlorine, there's the chlorine 35 isotope and the chlorine 37 isotope. For bromine, it's the bromine 79 isotope and the bromine 81 isotope. These are the two naturally occurring isotopes of these halogens. So that's why we see this pattern. We can actually distinguish between the two because there's a different abundance of these depending on our halogen. For chlorine, it's about 75, I think it's actually like 76-24, but we're going to make it nice round numbers here. 75% of all chlorine in the world is this chlorine 35 isotope. 25% is our chlorine 37 isotope, right? So that means that we would get a 3-to-1 ratio of the size of these two peaks here, right? So an M to M+2 ratio of 3-to-1 indicates there's a chlorine in our molecule. For bromine, these are just about 50-50. I think it's really 51-49, but again, using some nice round numbers here. So now we would get a 1-to-1 ratio. So again, if we see a molecular ion and an M+2 peak with a 1-to-1 ratio, that indicates that we have a alkyl bromide. All right, so in this case here, my M is 34, my M+2 is 33, This is just about as close to a 1-to-1 as we're going to see with our real data here. So this indicates that I have an alkyl bromide. All right, so for our fragment identity, I guess real quick, I'm going to still do my molecular ion peak was at 150. For my fragment identity, I'm going to include that M+2 peak, indicating I have a bromine. All right, that's going to be part of my fragment identity here. Now, with alkyl halides, the cool thing is, since they break at these bonds so reliably, we actually can do our number of carbon calculation. We just have to be a little bit clever, all right? So again, my molecular ion corresponds to the portion of the fraction of molecules containing the bromine 79 isotope. My M+2 peak corresponds to the proportion to the population of molecules containing that bromine 81 isotope. So let's take our molecular ion and we're going to subtract that isotope 79. 150 minus 79. This gives us an M over Z of 71. So this is our loss of Br. So this guy right here corresponds to our molecule. I don't know what this molecule is. I don't know how big it is, but I know that this thing right here corresponds to all of the carbons and all of the hydrogens, just missing that halogen. So because of that, I can take that 71 and its +1 peak, 71 and 72, and I can still do my number of carbon calculation. There's a chance that it may not work out beautifully, but a lot of times it does, right? So I'm still going to be able to do a number of carbon calculation using my 71 and 72. So again, now I'm going to take the 45 divided by the 839 divided by 1.1 all times 100. And I get 4.87 or 5. Okay, so now we can keep going here. Let's do our number of hydrogen calculation. We're going to take that molecular ion. We're going to subtract our bromine 79. We're going to subtract our 5 carbons. All right, so 150 minus the 79 minus 5 times 12. Oops. And we get 11. So C5H11 Br. Okay. Again, let's just be good and note here. As always, we're going to include a molecular formula and our proposed structure, just to make sure that we actually can draw something that has that molecular formula. So in this case, my alcohol, same thing down here. Honestly, I can give the same alcohol because I'm just proposing a structure. If I'm being really good and smart about it, we identified that this was a secondary or tertiary alcohol. So let's just go ahead and draw a secondary alcohol. And here for an alkyl bromide, just to make sure, is a 5-carbon alkyl bromide. Does that have the correct number of hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Excellent. All right. So this would be a legitimate molecular formula for an alkyl bromide here. All right. So for our poorly behaved spectra, what are we going to do? We're going to include now this fragment identity portion to our analysis, right? At the end, we're still going to arrive at our molecular formula with our proposed structure. Now we just got to figure out what at least one of these peaks downfield here is in our mass spectrum.